Hi everyone, my name is Chalisa and I am a PhD student at the University of Strathclyde in Scotland, UK. My project is focused on developing optical coatings for gravitational wave detectors and laser optics using next generation I-beam deposition technique. Here is the outline of my talk today. So I'll be giving an introduction to our group, to laser optics and gravitational waves and its detectors. I'll be talking to you about the technique that we use to fabricate our coatings, and of course show the setup that we have at the University of Strathclyde. I'll also show you the objectives, results, conclusion and outlook of my project as well. Here is our group, so we have Professor Stuart, who is our group leader and also head of the Biomedical Engineering Department at the University of Strathclyde. Here is myself and Dr. Marwa, and our project is focused on utilising ECR ion beam deposition for high laser damage threshold optical coatings, as well as coatings for gravitational wave mirrors. This is Callum, and his project is focused on piezoelectric coatings for sensors and also DLC coatings for biomedical applications. Here is Dr. Paul Hill and Gavin, and their project is focused on utilising RF-IBD deposition to fabricate mirror coatings as well as mechanical loss measurements for gravitational wave detectors. And this year is Curtis Talbot, and his project is focused on thermal annealing impact on optical performance of oxide coatings. For high power thin film optical coatings, they require optics that can sustain high power output from lasers. The optical coating is generally the limiting factor in the output of a high power laser system, and so there is an increased requirement for coatings with high damage threshold. As for the gravitational wave side of things, Albert Einstein predicted the presence of gravitational waves in the general theory of relativity in 1916. The theory revealed that massive accelerating objects like neutron star or black hole binaries would disrupt space-time, causing the ripple effect. This is where the waves of distorted space would radiate from the source. It is very difficult to detect these on Earth as the waves get weaker as they travel through the universe, and hence the detectors were designed. The LIGO detectors utilizes microsynth interferometer and Fabry-Perot cavity techniques. There is a high demanding key requirement for the coatings on the test masses or the LIGO mirrors, which are very low absorption and scarcing losses, high reflectivity, and low loss dielectric mirrors. And currently, the coatings that are being used at the moment are not reaching these requirements when fabricated by the typical commercialization system. And the technique that we use to fabricate our coating is ion beam deposition technique. How this technique works is that a gas is injected into the source, which is typically argon gas. The atoms are ionized and accelerated towards the target, sputters the target material and deposit this material onto the substrate. Ion beam deposition creates compact and durable films with properties closer to those of bulk materials, hence why this is the method of choice for high-performance optical coatings. In a typical ion beam deposition system, either a Kaufman type or an RF type sources are used. With these sources, the ions are extracted and accelerated using a grid system, which is a source of contamination for coatings. Whereas our system, we use ECR type sources. How this works is that a plasma is created by the help of a permanent magnetic field and a microwave, where free electrons can absorb the microwave power and continuously accelerate and ionize the gas molecules that was injected. This happens when the microwave frequency matches the angular frequency or the resonance of the electrons. The beam is then extracted through an aperture rather than a grid. The advantages of our ECR source is that it is gridless and filament free, which means it's a cleaner process. It is maintenance free, has low current, it's got 0 to 10 kilovolt extraction potential energy, which means it has a very energetic beam, and it can also be precisely controlled. And here's what the setup that we have at Strathclyde University. This is the RF ion beam deposition system run by Paul and Gavin. This is the second largest coating chamber in the world for gravitational wave coatings development, where the largest one is LMA Grand Coater. It is a 1.7 meter cubed cooled chamber, and it also has 16 centimeter RF ion source here. Recently, we just acquired a 2.2 million secured capital and personnel investment to create the Extreme Performance Optical Coating Centre, or EPOC for short. And this will be commissioned in September or October of this year. This is the industry best method, which is currently unavailable within the UK, and it will also be the largest ion beam deposition system in the world. This system is basically a large-scale RF ion beam deposition system where amorphous coatings can be fabricated for optics that weighs up to 200 kilograms. Currently, we have 3 ECR ion beam deposition systems at Strathclyde, and this is the prototype system with only one ion source. This system has actually demonstrated the lowest optical absorption ever reported in amorphous silicon thin film. You can also find this paper in PRL journal, published in 2018 as well. Here is the second ECR ion beam deposition system that we have, which is basically a scaled up version of the previous system. This system has 6 ion sources with 3 ion sources on either side of the chamber. We've added a rotational stage to the system to create a more uniform coating, and because it's a larger system, it's easier for us to create mixed material coatings compared to the smaller system as well. And this is what the sources look like when you take it outside the chamber. And here is our newest ECR ion beam deposition system. This system has 24 ion beams with conical targets, and it was developed in collaboration with Polygon Physics. With this system, it provides the flexibility to fabricate mixed material coatings with differing percentages, as we can control the beam property individually using LabVIEW. As for characterization, here we have the GIN system, which was commissioned at Strathclyde. Our colleagues at Glasgow University are also working on chirogenic GIN system as well. This system is used to measure the mechanical ring downs and determine mechanical loss angle associated with coating thermal noise. And here is the Photon RT, which is a spectrophotometer that is specially designed for optical coaters, with a wide range of wavelengths from 185 to 5,000 nanometers. This system will provide us with the transmittance and reflectance data, where we can then input into an optical fitting software called Scout to obtain the optical constants of our coatings. We also have access to other characterization within the university as well, for example, WDX, EDX, XRD, and AFM. Also, we are in collaboration with Glasgow University, who has the ability to measure sub-ppm absorption using the photothermal common path interferometry. Now for the objectives of my project. There are many parameters that we can change in order to tune the coating's properties for their needs. For example, we can change deposition temperature or even post-deposition thermal treatment. We can also use different sputtering gases or different percentage of gas mixture, as well as looking at different target materials. And the materials that we have looked at for gravitational wave, we've looked at germania, tellurium, titania, silica, amorphous silicon, silicon nitride, tantala, and zirconia, as well as mixed materials. As for our laser damage threshold side of things, we've looked at hafnia, scandia, silica, and mixed materials as well. For piezoelectric, Callum has looked at zinc oxide and aluminium nitride, as well as DLC for cardiovascular implants. And here are some results that I have accumulated during my PhD. So this is my most recent work, which is investigating the effects of different gas mixture has during deposition on optical parameters. We looked at different oxygen percentage in the background, which is shown in this graph here, and also looked at different percentage of oxygen as deposition gas. From this, we have found that as the oxygen percentage in the background increases, the refractive index of the film decreases. The same was also discovered for different oxygen percentage through the ion sources. I didn't show this here, but we also found that as the oxygen percentage increases, the bandgap energy also increases for both cases. Here we investigated utilising argon as sputtering gas versus oxygen from mixed materials scanned in silica. And also we looked at the effects of post-deposition annealing has on the optical constants. We can see here that as the annealing temperature increases, the refractive index decreases for both argon and oxygen sputtering case. And also as the annealing temperature increases here, the band gap energy also increases for both cases. And here we can also see that by using argon as a sputtering gas, it provided a lower overall refractive index and also a higher overall band gap energy than utilizing argon. This has showed that by using a different gas to sputter from a target, we can manipulate the optical parameters as well. As mentioned earlier, with our ECR ion beam deposition system, we have a world record for fabrication of the lowest absorption of amorphous silicon thin films, which is less than 20 ppm absorption at 1550 nanometers. And again, you can find this in PRL journal published in 2018. And from this, we have found that our coating has a lower loss at 1550 nanometers than the commercial coatings as deposited as well as post-deposition annealing as shown here. Finally, I also looked at mixed oxide for gravitational wave side of things as well, which is zirconia tantalum. We've chosen these two materials as both of them have high refractive index values at 1064 nanometers and 1550 nanometers. And by using mixed materials, this will gain the benefit of high refractive index and low mechanical loss materials without losing the required optical properties, which means that this will reduce the coating thickness that is needed, which then leads to the reduction of Brownian thermal noise, which is the main concern of a LIGO at the moment. Now for the conclusion, I have successfully commissioned and developed two ECR ion beam deposition systems during my time, and Gavin has successfully commissioned two gen system and one RF ion beam deposition system as well. We have investigated different materials for both laser optics and gravitational waves, and we've also investigated different parameters during and after deposition and investigate the effects it has on the coating's optical parameters. For our ongoing research activity for gravitational waves, we are investigating materials with corner-sharing properties, including germanium oxide and also germanium titanium alloys, where the titanium will be used to increase the germanium refractive index. This is based on the findings published by Paisley in 2019 while studying the zirconia doped tantalum films. He showed that the mechanical loss is correlated to the fraction of corner sharing and amorphous structure, and also that annealing increases the corner share polyhedra and decreases the edge and face sharing polyhedra. As for the laser optic side of things, I'll be investigating other mixed materials, including different mixing percentage and also the effects of post-deposition thermal treatment on the optical properties and laser-induced damage threshold as well. Thank you so much for your time and thank you so much for listening. If you have any questions, please don't hesitate to ask or get me an email. Thank you so much.